Batteries operate under a current of electrons and ions, which migrate back and forth from the electrodes. Electric behavior, therefore, can be analyzed by measuring the resistance, or better, the alternating current resistance, the impedance. Since impedance measurements are carried out at a series of frequency, it is also reflect time constant. And because several mechanisms in the battery are time dependent, it is possible to deconvolute these mechanisms and processes by impedance spectroscopy. So let us see how impedance spectroscopy, or better, electrochemical impedance spectroscopy, EIS, works, starting with the system we would like to analyze. Electrodes play an important role in the study of the electrical properties of solid and liquid electrodes and electrolytes. They can give rise to undesired polarization effects. To understand the electrolyte and electrode properties, it is of utmost importance to identify these polarization effects. A very simple setup for measuring the conductivity of a medium is shown here. With DC measurement techniques, then, it is possible to obtain the conduction of the electrolyte if they obey Ohm's law, where the resistance R is equal to the voltage V divided by the current I. For most solids, however, Ohm's law does not apply. In these cases, it is more appropriate to use alternating currents, AC techniques, to measure the conductivity. Once using AC techniques, the choice of the electrodes is important in terms of blocking the electronic part. This means that the direct electronic pathway is being blocked to prevent electrons to enter the electrolyte. Note that, on the other hand, by selecting a metal as electrode, an ion cannot penetrate this electrode. This ion then can only be reduced by accepting an electron under an electrochemical reaction. This is what is shown here in the case of a copper electrode submerged in a copper sulfate solution. In contrast, non-blocking electrodes, i.e. reversible electrodes, allow the charge carriers under study to move freely from the electrode into the electrolyte and further down, back into the opposite electrode. In general, it is possible to obtain relevant data of the mass and charge transport, electrode and electrolyte polarization by means of impedance measurements. This is often referred to as AC conductivity measurements or impedance spectroscopy, where the frequency of the applied voltage or current is being varied. Therefore, the frequency is an important parameter, but also temperature, electrode and electrolyte compositions and electrode size and distance. The AC technique then allows in principle to separate between the electrode and electrolyte polarization effects by using a so-called equivalent circuit. Then by clever changing the parameters, it would be possible to assign the various elements in the equivalent circuit to a certain physical or electrochemical process. Note that each process has, by definition, a characteristic time, the time constant. This time constant can be simply reflected by a capacitor. The progress, then, of the process is determined by a parallel resistor, giving rise to an equivalent circuit of a resistor parallel to a capacitor, the well-known RC circuit. This circuit also reflects the difference between a Faraday current, IF, and a non-Faraday current, INF. The Faraday current will become constant after a certain time, whereas the non-Faraday current will not. To characterize the electrochemical process, the system is analyzed by impedance spectroscopy using a small amplitude AC signal by varying the AC frequency, and therefore it is called impedance spectroscopy or electrochemical impedance spectroscopy, EIS. This will thus be analyzed by the measured complex plane, referring to the impedance data or admittance data. This, after a short introduction to the complex impedance and admittance of a system, several equivalent circuits and the relation of the circuit's components to the physical processes are shown. A sinusoidal voltage V at time t is expressed by V times t equals the maximum voltage, Vmax, times the sine of the angle frequency omega times time t. For the current I and the angular velocity omega equals 2 times pi times the frequency f. The induced current at time t, IT, in this cell exhibits a phase shift phi, giving IT equals I max times the sine of the angle frequency times t plus the phase shift phi. Before going further, let's step into some mathematics. Imagine you have a function of y equals the sine x plus the cosine x. We can calculate the first and second derivative of this function. It turns out that the function y is equal to minus the second derivative of this function, minus y. Imagine now that we have a function y equals e to the power of g times x, with g the imaginary number for which the square of g minus 1 is. It means that here too the function y is equal to minus the second derivative of the function y. This leads to the mathematical definition that it equals e to the power of g times x, and this will be the basis for the measurement of impedance spectroscopy. Electric behavior is assigned by measuring the resistance, or better the alternating current resistance, the impedance. Impedance measurements are carried out at a series of frequencies. That means we use the voltage as V, T, and the current I, T, with A, the phase shift phi. We can now rewrite the voltage and current in imaginary numbers. According to Ohm's law, the impedance is the voltage divided by the current. Therefore, the impedance is the complex potential divided by the complex current. Similarly, the complex admittance Y is defined as the quotient of the complex current and potential of the cell. Thus, the admittance Y is the reciprocal of the impedance. Note that Z prime here and Z double prime do not stand for the first and second derivative, but reflect the real and imaginary part of the relation. According to Ohm's law, the impedance Z can be drawn now by relation with imaginary numbers, not surprisingly called complex numbers. The admittance, the inverse impedance, can be written in a similar way. In the complex plane, we could plot y double prime versus y prime and represent the admittance by a vector of amplitude absolute y, making a phase angle with the real axis y prime. A similar strategy is followed for the impedance in a plot of z double prime versus z prime. An impedance meter usually measures the imaginary part of the impedance, z double prime, versus the real part of the impedance, z prime, at various frequencies. So let's see how that works then. In all, it looks quite complicated, mathematically seen. Here we look at the spectrum measured on a circuit where a resistor Rs in a series with a system of a resistor Rp in parallel with a capacitor Cp. This last system is usually called an RC circuit. The spectrum then is a semicircle shifted from the origin. Here the resistor Rs is responsible for that shift, and the semicircle comes from the RC circuit. The final touchdown at low frequency on the right hand side is the overall resistance, hence Rs plus Rp. From the maximum of the semicircle it is possible to calculate the capacity of the capacitor. Now every RC circuit will then be placed in series, will give us an extra semicircle. These semicircles are usually overlapping. Each of the RC circuit mimic a specific process with a characteristic time, which can be analyzed by the frequency at the top of the semicircle.